All right, guys, so this lecture today is on acceleration. So, before we talk about acceleration, we're going to need to talk about velocity. I'm going to make myself small in the corner and we will get started. So, velocity. All right, let me scoot over some. Okay, there we go. Velocity includes the speed of an object and the direction of its motion. So, velocity has the same units as speed does. It's meters per second. The only difference between velocity and speed is that velocity includes direction. So velocity is speed in a certain direction. I'm going 3 miles per hour north. I'm going 4 miles per hour south. I'm going 6 miles per hour east. I'm going forward at a rate of 1 mile per hour. So velocity is speed in a direction. So velocity includes the speed of an object and the direction of its motion. So the only difference between speed and velocity for this course is that speed does not include direction and velocity does. When you're graphing those and when you're working with some position time and velocity time graphs in later courses, that's going to matter because it's going to make velocity a vector. So it's going to make us be able to graph velocity, whereas we can't graph speed because we don't know which direction it's going in. All right, so this is the same thing again. Apparently, I really wanted to drive this point home. So velocity has the same units as speed, meters per second, and the velocity will change even if the speed remains constant. So on an escalator, the velocity is the same. The speed is, the speed is the same. The escalator always goes the same speed. But the direction of the two escalators is different. One goes up and one comes down. So because of that, they have different velocities. Even though they're going the same speed, they're going in different directions, so they have a different velocity. All right, so I don't know why that momentum slide is there. Let's delete that. Doesn't belong there. All right, so acceleration is the rate of change in velocity. So since velocity includes speed and direction, acceleration can be a change in speed, acceleration could be a change in direction, or acceleration could be a change in speed and direction. So if I am riding a bike and I'm going at a constant pace and I go in a straight line, I don't have any acceleration. My speed is staying the same and my direction is staying the same. If I'm riding a bike and I speed up, I keep going in a straight line, but I get faster and faster and faster, I have acceleration. My speed is changing. If I'm riding my bike at a constant speed and all of a sudden a car comes out in front of me and I push my handbrake on my bike, I have acceleration. My speed changed. If I'm riding a bike and I see a pebble in the road and I swerve my handles to get around the pebble, my acceleration changed. My speed probably didn't change. I probably kept at that same constant speed, but I moved my bike. I changed the direction. So I had a change in acceleration. All right, so things speeding up and slowing down have acceleration, and that's kind of hard to understand. So our velocity is speed in a certain direction. So when we are going forward, our acceleration and our velocity are going in the same direction. The light turns green, we're getting faster, and we're speeding up in the same direction. So our acceleration and our velocity are going in the same direction. But all of a sudden, the light turns yellow. Our velocity is still going forward. Our speed is still going forward, but we're slowing down. So our acceleration is going in the opposite direction. we use the common term of deceleration for this. That's technically not a correct term. It's acceleration in the opposite direction. So if we were accelerating north here, we would be accelerating south here. All right, so calculating acceleration. So acceleration is measured in the units meters per second squared. And acceleration is a change in velocity over a change in time. Your change in velocity is the final speed you were going minus the very initial speed you were going. So that means our acceleration is equal to our final speed over our initial speed all over time. All right, so let's take a look at some example problems. These are already worked for you. So let's look at what positive acceleration is. So we have a picture of an airplane here. We live by the airport. We see a lot of FedEx planes and a lot of commercial planes coming and going. So let's use a plane. Our plane takes off. We don't know what our plane's initial place was, but we know its initial velocity was 0. It took off from rest. So that might not always be given. You might have to look for words like from rest, or it comes to a rest, or it comes to a stop, meaning its final position is 0. But we'll get to that. So let's look at this one first still. So a plane takes off from rest. Its initial position was 0, and it reached a speed of 80 meters per second in 20 seconds. So it started at 0 meters per second, and it reached a speed of 80 meters per second in 20 seconds. So my final speed was 80 meters per second. My time was 20 seconds. So when I did the math, I got 4 meters per second squared. That means the plane's acceleration is positive. It's speeding up. It's getting faster and faster and faster and faster. And when we get answers in science, it's always nice to decide if our answer makes sense. So does it make sense that a plane's acceleration is positive and it's getting faster and faster and faster as it tries to take off the runway? And the answer is yes. If it doesn't get faster, it can't take off. So that answer makes sense. So it's a viable answer, and it's the solution. All right, let's look at the other type of acceleration. So I said we could have negative acceleration, or acceleration in the opposite direction. So Susie was riding her bike. She was riding her bike at the speed of, or at a velocity of 3 meters per second north. And she saw a frog in the road and pressed on her brakes and came to a stop. It took Susie 2 seconds to come to a stop. So she started out, her initial velocity was 3 meters per second. And when I read the problem, I said she came to a stop. So she stopped. Her final speed was 0. All over, how long did it take her? It took her 2 seconds to come to a stop. So we're going to say 0 minus 3 is negative 3, divided by 2 is negative 1.5 meters per second squared. Acceleration is negative. So what does that mean? If our acceleration is negative, it can mean one of two things. It can either mean that Susie is A, slowing down, or Susie is B, changing directions. The formula or the problem didn't say anything about Susie turning her bike, so she's still going in the same direction. But it did say that Susie slowed down. So that answer is viable because negative 1.5 means she slowed down, and we know that Susie did slow down because she eventually stopped. So negative 1.5 meters per second squared is a viable answer, and it is our solution to our problem. All right, so let's look at a few more problems. A skateboarder has an initial velocity of 3 meters per second west. He comes to a stop in 2 seconds. What is his acceleration? So our initial velocity, it says, is 3 meters per second west. So let's highlight that, 3 meters per second west. And I'm going to make my initial velocities. It wants to make them blue. I don't want to make them blue. Let's send to back. And let's change that color to, I don't know. How about purple? Ooh, we can't see purple. Yellow. All right. So our final velocity, our initial velocity is yellow. He comes to a stop. Okay. So a stop, we need to highlight that, right? So I need to insert another shape. Oh dear, that's not what I wanted to do. All right, he comes to a stop in 2 seconds. So his initial velocity was 3 meters per second west. He came to a stop, so his final velocity is 0 meters per second, and our time is 2 seconds. When we do our math, we get negative 1.5 meters per second west. So that means he's slowing down. That's right. He's slowing down. Let's look at the next one. An airplane starts at rest. So our initial velocity, how fast was it going when we started? It was going 0. It accelerates down the runway for 20 seconds. All right, seconds is time. Put that in the bottom. At the end of the runway, its velocity is 80 meters per second north. Okay? 80 meters per second, end of runway. I think that's my final velocity. I'm going to plug that in there. What is its acceleration? It comes out to 40 meters per second squared north. That makes sense. The plane is getting faster and faster and faster, so it can go into the sky. All right, a cyclist starts at rest and accelerates at 0.5 meters per second squared south for 20 seconds. What is the final velocity? All right, so my final velocity is equal to acceleration times time plus my initial velocity. If you have trouble with these problems, you can do them like you would do a speed triangle. I don't have the capability right now. I don't have a pad with paper. If you watch the other video, though, you can see where I work these in a speed triangle format. So we have 0.5 meters per second south as my acceleration. I'm going to plug that in. We have 20 seconds as my time. My final velocity is what we're looking for. And we start at rest. So my initial velocity is 0. So when we plug it in, our final velocity was 10 meters per second south. So that's how fast we got.